Hi everyone, I'm Chris Saxon. I'm part of Stephen Feuerstein's Oracle Developer Advocate team. My job to help you get the best out of Oracle Database and hopefully have a little bit of fun whilst doing so. So with that in mind, we're going to be looking at how to read execution plans today. So the session last month, we talked a bit of detail about optimizing queries with range-based criteria in them, dates between, from, and to dates and so on. I thought we'd bring it back down a notch this time, just focus on some of the basics, just how we actually read an execution plan at all to start with. So as always, this is your chance to ask questions. So if you've got any, just put them in chat. If you want to speak and actually talk to me, that's fine too. Unmute yourself. If you're not talking, please do keep yourself on mute. As always, the recording will be available. It'll be alrighty then. So as I said, welcome and let's get going. So SQL is fantastic. One of the great powers of it is its declarative nature. You tell the database the result you want, and it figures out the best way to get it. But if it's figuring out the fastest way to do something and your query is too slow, this gives you a bit of a problem. How the heck do you make it faster, right? The database has taken charge of all the optimization process. So what do you do? Well, if you start asking around about how to make SQL faster, improve its performance, you'll ask, some expert, and they'll say something like, look at the execution plan. And you're like, okay, so you duly go out and get the plan for your query and start looking at things, saying joins, full table scan, and so on. You're looking at like, well, how the heck does this help me? I've no idea what's going on here. I really don't know how this helps me optimize my query in any way. So what we'll do is look at some of these things. Now, the first thing to note is the plan is like the driving directions for the optimizer. So if you're planning a route, you'll get your map out and you draw some arrows on it. Well, these days you'll get your favorite mapping software to draw the route on it. But you'll end up with a series of arrows on your map showing you the route you need to follow. So what we really want to do is draw our arrows on our execution plan to see what's actually going on. So just to relate it back to the real world example. So I live in the UK, and once a year, or at least once a year, I fly out to San Francisco, usually for open world. Not next year anymore. We're moving to Vegas for open world next year, but last few years it's been San Francisco. And if I want to follow these directions, it's pretty obvious. I've got my map. It says, leave my house, take the train or whatever, get to the airport at London, get on the plane, fly to San Francisco. Fairly straightforward. But with an execution plan, you've got something that looks a bit like this. Like say, full scans, joins, and so on. You're like, well, how does this help us? How does this help us figure out what's actually going on? You're like, those don't look like driving directions. There's not any obvious series of arrows that I'm going to follow to help me figure out how to get from through the plan, how I traverse through it. So what we'll do is show you the process for doing that. Basically, we've got our execution plan here. We're going to start drawing some arrows on it, show some examples of how you can do that. And at the end, we'll then walk through some examples of some kind of common problems or things to look for in an execution plan and how you might resolve them. All right then, so before we jump into the details of how we actually draw these arrows on, a bit of background. So the thing to notice here is the execution plan is a tree. Now, of course, I don't mean like your plant that you'll see out in your garden. We're talking about the data tree or a directed acyclic graph. So each operation has at most one parent and can have many children. So the parent-child relationship in an execution plan is determined by its indentation. So the further indented to the right an operation is, the more likely it is to be a child. And particularly with these text-based plans, it is really, really important you preserve this indentation. Quite often, you'll see plans posted on forums and so on. They look kind of like this. Everything is just perfectly left justified, and all the operations appear kind of aligned with each other on the left. This makes it really, really tricky to figure out what's actually going on here. So simple plan like this, 2 tables, we can probably cobble it together. But imagine there's 10, 15, 20, 30 lines in this execution plan. becomes quite tricky to figure out how the things relate to each other. You can spend 10 or 15 minutes just trying to piece together what is the child of what. And in some cases, it's really not very clear. So if you're sharing text-based plans like this, absolutely critical. Make sure you preserve the formatting and use a fixed width font such as Courier so we can see the indentation clearly. Okay, so we can see parent-child. How do we know what the parent of each operation is, or its children? So let's start with this hash join kind of in the middle here. So the parent of an operation is the first one above it that is indented to the left. So we look at that hash join, the first one above it to the left is that select statement. So that is its parent. The children of it are those indented to the right that are below it. So the full scans are both the children of this full table, of this hash join, sorry. Okay, so we've got the parent, we've got those children. What about the full scan of the colors here? What are its parents and children? Well, the parent is the first operation above it that's indented to the left. So that's that hash join. Its child, well, it has no operations below it that are indented to the right. So the bricks, the full scan of the bricks table below it is its sibling. It's not a child. So all the operations below it indented to the right up until the next one, its sibling, that is at the same level, same depth of indentation, are its children, and then we've got sibling, and then we repeat the process. Okay, so we know the parent-child relationship there. What we could also do is draw the plan out like this, like you draw a typical hierarchy. Select at the top, hash join, and then it's got its two scans below it of the two tables. Right, so we can kind of starting to piece things together a bit more here. How do we actually follow the process? How do we traverse through this plan? Well, what we do, whenever generally traversing a hierarchy, you start at the top, the root, and then work our way down. So we work the way down to the first unvisited leaf. So that is right down to the bottom. So that would be that full scan of the colors table. Once you've got there, you then go back up to the parent of this operation. And having done that, you then repeat the process. So we got to the join, go down to the next unvisited leaf, which would be the full scan of colors, go back up to the parent, and so on and so forth through the plan. So this is the basic, this is a depth-first search of the tree. So start at the top, go down to the first leaf, back up, and keep recursively doing this. So what I'm going to do is walk through a few example plans to show you how this works in practice. Have we got, or what questions or comments do you have at this point before we jump into that? Nope, no questions. Okay, from Peter, how to see them in SQL Developer. Very great question, Peter. I'm going to have a demo later on where I'm going to be showing these plans in SQL Developer and show you how to get these as well. So I'm going to stick with text-based plans like you might get with DBMS Expand just for the slides. We will move to a demo later that uses SQL Developer. So stay tuned for that. Okay, so let's bring up our plan again. So this is just our basic two-table join. So remember, first thing we need to do, start at our select statement at the top and travel down the plan to the first unvisited leaf. So that is the top operation in the plan with no children. That's the full scan of the colors table. So we go down to that. Once we've done that, read all those rows, we pass them back up to its parent, the hash join. Build the hash table here, and then looks for the next unvisited leaf here. That's the full scan of the bricks table. Read all the rows out of that, start passing them back up to the hash join, find, the matching rows, and return them to the client. So far, hopefully, fairly straightforward. Let's level things up a bit, make it a bit more complicated. We'll now go for a 4-table join. Seems a bit more complicated, but the process is exactly the same. You start with that select statement at the top, travel all the way down the plan until you get to the first unvisited leaf. That's the top one in the plan that has no children. That's the full scan of the colors table. Once we've got there, read those rows, pass them back up to the hash join, build the hash table, look for the next unvisited leaf. Well, that's this full scan of the toys table. Read those rows, pass them back up to the hash join. Now, at this point, we have read all the rows from the children of this hash join operation. So there are no more unvisited leaves below it. So rather than looking for the next unvisited leaf, we then just go straight up to its parent, that hash join. So we've joined the first two tables. We're now building the hash table from the result of those. Then look for the next unvisited leaf. That's down to the pens table. We read all the rows out of that, and then continue on through the plan, following a little kind of snaking pattern that looks a little bit like this. So a bit more complicated, but hopefully still relatively straightforward. Let's level things up again, go for another more complicated example. This time we will again have 4 tables in the plan, but they're not all going to be joined in the same way, or they're not going to be combined in the same way. So we've got a plan that looks something like this. And you can see we've got a union operation there. There's something a bit different going on. So this time, again, start at the top, that select statement, travel down the plan to the first unvisited leaf. That's that colors table. Read the rows out of that, pass them up to its parent, the hash join. Now from here, we then need to travel down the plan to the next unvisited leaf. That is all the way down, and that full scan of the bricks table. Now, these scans of bricks, toys, and pens are all at the same depth. They are all children of that union all operation. So we'll walk down reading those rows. Do note, there is an optimization available. If you run this query in parallel, the database can read all 3 of those tables at the same time. In normal serial operation, it will do one after the other. But either way, we're reading those rows. It'll pass them back up to the union all operation, which will combine them into a single result set. At this point, there are no more unvisited leaves in the plan. So all we need to do is just walk all the way back up it, passing the rows back to the individual operations so we can combine them, give our final result set. Okay, so it's a bit more complicated, but hopefully still relatively easy to follow. Let's level up again. Now, I'm going to show you a plan that looks much simpler at first, but is a bit different. So let's have a look at this plan. Okay, we've just got 2 tables in here, but it looks a bit different to our original 2-table join, right? So what's going on here? Anyone notice something a bit different or a bit suspicious about this plan? So the sort, yeah, is a bit different. Group by. Okay, so the sort and the group by, Tone's got it. Scalar Subquery and select list. I knew you'd get this, Tone. Yeah, so the thing to note here about this that's different is there's no join operation, right? Where is the join in this query? Or someone's saying missing a join condition. You know, looking in that execution plan, there is no join there. And as Tone correctly identified, the query that we got that generated is something a bit like this. So the key thing to note here is I said we had this rule of we walk down the plan and read the first unvisited leaf. Things change a little bit when it comes to Scalar subqueries. So the select clause is processed after the from clause. So we need to get all the rows out of this colors table, and then we start passing them to this subquery. So we're passing the rows from the colors table into that subquery. And if we look at the execution plan, well, we see, hang on, colors table's down at the bottom. And I was like, hang on, didn't I say we go down to the first unvisited leaf, which in this case looks like the bricks table, right? No, this is one of these scenarios, it's the exception that proves the rule. So there's a couple of reasons I'm showing you this. First up, just to kind of make you aware of this scenario. But secondly, for every kind of rule or guideline or principle I show you, there's going to be at least one edge case where that doesn't apply. And this is part of what can make SQL optimization tricky, is you've got some guiding principles, so to speak, but there's exceptions all over the case, all over the shop. You know, you can always find an unusual scenario or something which kind of breaks everything that you've learned. So you need to think about how SQL actually processes it, understanding the SQL engine and how it works generally is a good principle as well. Won't cover that today, but maybe we can discuss that in a future episode. So the thing here, as I said, colors tables in the from clause. So the first thing we'll do is read the rows out of that, pass them back up to the select statement. Then for those rows, we will run the scan of the bricks table. So we'll start reading that. Now, the interesting thing to note here is this scan could happen as much as once for every single row we get out of that colors table. So we could end up running this full scan of the bricks table a lot of times. Now, there are some optimizations in Oracle database, which means usually it's not quite that bad, but in general, it is likely if you've got a Scalar Subquery, you will run that many times. So in this case, we're going to full scan that bricks table more than once, quite likely. Okay, so there was a few kind of example plans that we walked through showing the process that the database follows to get through them. What questions or comments do you have at this point? Okay, what does the predicate section show? Okay, so good question, Judith. The predicate section shows you when the predicates are applied. So you've got conditions in your where clause, so things like column equals value or join criteria and so on. The predicate section shows you where exactly in the plan those criteria were applied to the operations. I've not got any examples in the slides themselves, but when we come to SQL Developer, we can talk about that in a bit more detail. All right then. So, okay, so those are the examples I wanted to walk through here. We can see the basis of how to follow this. So the question now is, well, how does this help make our queries faster? And how do we try to improve things? So just another comment from Judith. In all the versions, example 8i, the Scalar subqueries did not appear at all in the plan. I really hope no one watching this is using 8i still, but it's a good point. Like I say, be aware that everything I say just may change in future releases, and there's always exceptions. So there are situations which may not follow exactly the rules, principles, guidelines I've discussed here. So yeah, one of the harder aspects of SQL tuning. Okay, so let's see, how can we make our SQL faster using this plan? You've got the plan, you know the route the database followed through it. How does this help us? Well, let's return to my example traveling to San Francisco. This is a long journey, and I'm coming to you and kind of going, this took forever. How can I help me make this faster? Come on, Chris. Come on. How can I get there quicker? If I come to you and say that, chances are your answer is going to be, well, I don't know, right? I don't know how you can travel quicker, at least knowing nothing more than I got from London to San Francisco. There's a whole bunch of other questions that you would want answered before you can provide any kind of meaningful result that would actually is likely to help improve things. First up, things like, well, how far did I actually travel? So distance between them is something like 5,000 miles. So that is quite a long distance. And the thing to note there is, no matter how fast a transport method I use, it's going to take me a while to do this journey. And if, so basic laws of physics and that, we can't travel at the speed of light and probably never will be able to. So if I want to make truly huge gains, then I perhaps need to think, is there a way we can eliminate this journey time altogether? If we're traveling 5,000 miles, can we not travel that? Maybe instead of living in the UK, I can move to San Francisco. Okay, that's a big effort, and I'm probably not going to do that. But it does mean I can get that, I don't have to travel halfway across the world. Or maybe, I won't travel. I won't go to open world. I'll stay at home. That's probably not going to happen for various other reasons. My boss won't let me. Or maybe I could stay at home and give a WebEx, so I don't need to travel. The key thing here is when you're processing lots of data, and particularly if you're returning them to the client, well, you've got to ask yourself, are your performance goals here reasonable? Every now and again, you get someone coming up and saying something like, I've got a query that returns 10 million rows, takes 30 minutes to run. I need it to run in under a second. And you just got to think, well, is that actually plausible? Processing 10 million rows is going to take a little while. Now, granted, we could probably get it right down from 30 minutes, maybe down to, for example, 30 seconds or something like that. But fundamentally, if you are processing huge gobs of data, your query is going to take some time. So think, is there a way we can process less data? Do we even need to run this query in the first place? So you've got really long running queries, process lots of data, and you need to improve their performance. Try and find ways to just not do that work. So there's a good principle to start with. Okay, so we know I've got to travel a long way. So the next thing to look at is, well, how long did this take me compared to how long it was predicted to take me? So the flight time was predicted at around 11 hours. Journey time was actually 10.5 hours. So actually half an hour quicker than expected. So, this estimate's fairly bang on. So in terms of the flying, getting commercial airliner, we've done reasonably well in terms of estimated time versus actual time. If the estimate was 11 hours and actually took me over 30, then maybe I could have chosen a different flight, which would have been more effective. So if what we're estimating is close to what we actually did, then that's a good match. Similar when it comes to processing data. Your execution plan, look at the rows we're processing. If the number of rows the database is estimating is close to the number of rows it actually gets, chances are it's come up with a reasonable plan. Or perhaps a better way to think about it is, if those estimates are way out, there's a good chance there's a better plan. If the database thinks it's going to get 1 row, but actually gets 1 million rows, probably a better plan available. So look at what the database thinks it's going to do versus what it actually does. How do they stack up? Then finally, of course, we've looked at estimates here kind of okay. We know I have to travel that distance. I'm not moving to San Francisco. How else could I have taken this journey? What other routes, transport methods were available? Well, a lot of those are going to be a lot slower. Maybe I could travel by hot air balloon or something. Clearly going to be a lot slower. To be a lot faster, I'm probably going to do something like charter a private jet. I'm just traveling by commercial airliner here. If Larry's kind enough, he'll charter me a private jet from a local airfield, and maybe I can halve the time it takes to actually do this journey. But is that really cost effective? Chartering a private jet is going to be expensive. Okay, so that's another thing to think about when you are tuning your queries. How can you create other routes? So common example is creating an index, but some of the more some things you can do or create to improve performance, things like partitioning, in-memory column store, and so on, do have additional cost associated with them. At which point you've got to ask yourself a business question. Is the business benefit we get from using those features, the faster query, worth the extra cost? And this isn't me saying you should go out and buy these. The point is, you need to assess how much does it actually cost you to work around these issues, in terms of developer time or, having the customers live with slower queries versus how much does it actually cost to buy these kind of things. And this doesn't just apply to Oracle database. Too often people look at the sticker price of something and go, oh, that costs money. We can do it for free, i.e. ourselves, and end up costing themselves more money in the long run. Whereas you say, well, in-memory costs us this, but the performance gains we get are Y, and we think that translates to Z business benefit. You can then do analysis. Well, is X greater than Z, the cost greater than the business benefit you expect? So think about that. Don't just think in terms of the sticker price of things. Think about how much business benefit do you get by using additional tools. Okay, so those are questions when I'm flying. How does this relate to SQL execution plans? So various questions you can ask here. So first thing is, row estimates. Are they accurate? Is the number of rows the optimizer is predicting close to the number of rows it actually gets? If they're close, then there's a good chance that you've got a good plan. If they're way out, there's a very good chance there's a better plan available. So that's just looking at how to access the tables and how to join them. We also need to look at how much work it actually took to do though, to read those rows, and that's how much I/O you did. So this is a term, comes under various names in Oracle database: consistent gets, buffer reads. They all kind of mean the same thing, which is logical I/O. How many times did we have to read some data? How much I/O did we have to do to read those rows? All other things being equal, the query that does less I/O will be faster and more scalable. Again, it's not always 100% true, but generally speaking, this is one of the key metrics you want to tune, you want to look at. How can we do less I/O? Okay, so we've looked at those, and those figures, our estimates are good, I/O reads are reasonable for the work that we're doing. Can we find a way to access the rows more efficiently? Can we create an index? Can we do things like reorganize the tables, table clusters, partitioning, blah, 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 blah? How can we read those rows more efficiently? How can we do less I/O to read the rows that we want? So that's the thing to look at there. Finally, of course, it's important to remember, response time is king. How long does it actually take to run your queries? The figures for all those previous things could be bad. The estimates could be way out. We could be doing lots of I/O, and we're doing full scans all over the place. If the query runs in a tenth of a second, who cares? If the customer's happy, that's fine. Equally, all those figures could be good, but if the query takes 10 seconds to run, that's probably not good enough. The key point here is the customer doesn't care how many logical I/Os your tuning efforts save. They care that the query went down from 10 seconds to less than a second. So the previous 3 questions are important to help you decide what you can do to make your query faster, but the final thing is the thing that you really need to pay attention to in terms of customer experience. How do they view what's actually going on? Okay, so I've got a question from Ingrid. How much off is too much? I guess you're referring to row estimates there. Keep that in mind. We'll come back to that in a little bit. Like I say, I'm going to show some demos of some execution plans, and we'll look at what we can do to make them run quicker. So there isn't a hard and fast figure, but generally speaking, once you're more than an order of magnitude out, so we've estimated 100 rows, you've got 1,000 rows or more, it's a sign that you want to start thinking about things. So once you're more than an order of magnitude difference, then start thinking about things. So Ravi, which is generally more bad, logical I/O or physical I/O? So that's a good question. So point here is that all physical I/O is contained within logical I/O. So let's say we do 1,000 logical I/Os. It could be that they're all from memory, or it could be that all of those actually do disk reads, physical I/O. So physical I/O is a lot slower, but it is dependent on things like, is the data cached? And generally, you don't really have much control over that. So I think you look at the logical I/O, because that will include your physical I/O, essentially. And then, so you tune the logical I/O, and hopefully the physical I/O sorts itself out. But physical I/O is substantially slower than logical I/O because it's actually from disk. I know disks are getting a lot faster, SSDs and so on, but they're still orders of magnitude slower than memory. So that's the point there. So what other questions do people have at this point? No other questions at this stage? Okay. So before we jump into some demos, one of the things I wanted to mention. So far notice I've been talking about execution plans. There are also explain plans. Sound very similar, they are very different. An explain plan is a prediction about what the database might do. And critically, it doesn't include information such as how many rows we read, how many logical IOs we did. To know whether the plan is right, you really need the execution plan, the stats, the runtime stats for how it performed when it actually executed, when it ran. So there are various techniques to do this. I'm just going to mention briefly DBMS Expand, because I think this is the best one if you're sharing stuff with other people, posting on forums, emailing for help, and so on, because you get that nice text output that we've been looking at so far. The key thing here is you want this gather plan statistics hint, which captures the row IO information, and the all stats format, so it actually displays that. The gather plan statistics hint captures that information. The all stats format displays that information. So once we've done that, you'll get some extra columns on your plan. So there'll be can be a whole bunch of them, but the core ones will be these, and we'll just walk through these kind of quickly. So starts, fairly straightforward. How many times did we actually do this thing? We did each of the things in this plan here once, but we could do them several times. Next, E rows, estimated rows. How many rows did the optimizer think we would get? And how does that compare to the A rows, actual rows? How many rows did it really process at the particular time? Next up, A time, actual time. How long did it take to run this? And buffers. So this is your IO. So let's say also known as consistent gets, buffer reads, and so on. How much work did we do to process all of these things? So if we look at the ones on the left, these are all specific to that particular line in the plan, that particular operation. So we're saying this second one here, we started it once, we estimated 68 rows, we got 56 rows. So 58, 56, pretty close. That's a reasonable guess, reasonable estimate for how we did. So what you're looking at here is, are these close? Now, one little wrinkle. You want to multiply the number of starts by the estimated rows and see if that equals the actual rows. We'll see an example later where that's different. So start times SE rows, is that roughly equal to A rows? Things on the right here are all cumulative. So that is the duration or the work for that particular line in the plan plus all of its children. So to find out the total number of buffers here, we don't add all of these up to get a figure of around 100. No, the total is the top line. So we did just 24. To find out how much work we did for this particular step, you need to subtract off the buffers operations for its direct children, which is just the operation below it. So 24 minus 24, no buffers for that particular step in the plan. Similarly for times, we need to subtract them off. Notice with DBMS Expand, times are all round, the granularity here is hundredths of a second, which may not be granular enough for really fast queries. So we'll see in SQL Developer how you can get a bit more accurate than that. Okay, so I can see the few comments come in the chat, so let's just look at those before we move on. All right, so Tone, a logical IO is a close by memory read from SGA. A physical IO is a further away read that can still be from memory, i.e. flash memory or actual physical disk. The latter would take more time. So thanks, Tone, for showing that and clarifying. Okay, Peter, can you share the query again? Was a bit quick to write it down and did have some comments in there. Which query were you referring to, Peter? Okay, so Daniel, is there a formula to calculate a reasonable time for the steps shown in the execution plan? I'm not aware of a good formula to kind of calculate this. I mean, one of the big drivers is how many rows you're processing and how much IO you're doing, which depends on things like how fast your underlying hardware is. It'd be really difficult to come up with a specific formula. Generally speaking, one of the points I said about these A times being of hundredths of a second, when we're processing small amounts of data like this, it takes well less than a hundredth of a second to actually do most of these things, as we'll see in in some examples in a minute. So Peter, the query to get the additional text output you just answered. Oh, so the one on the previous slide. I will, rather than do that, I will show you something in SQL Developer in a minute, Peter, okay? Also, all the scripts and demos I'm going to show you, they are all in live SQL. I will give you a link to that at the end of this session. So if you hang around, there will be a link to live SQL where you can get everything I've shown you today and play around yourself. So don't worry if you haven't captured it. And of course, as I say, we are recording this, so you can come back and review it later as well. Okay, what other questions or comments do we have before we jump into some examples of bad plans or plans that are maybe not quite right? So Judith, I think the hardest tuning question is this: how can we know whether a query can or cannot be further optimized? So that's a good question. And of course, one of the answers is you can almost always make things a bit faster, a little bit faster. The question is it worth the effort of making it a bit faster? Now, different people have different perspectives on at what point is good enough. And really, this is where really I think it's important to work with the customers, the business, and understand what your tuning goals are. You know, if they're happy with response times of 1 second, and your systems that you've got can cope with that load comfortably, then you can stop. Whereas if other businesses may need response times of sub a tenth of, less than 0.01 of a second, it entirely depends. And this is where you need to work with the customers, the business, so you can prioritize, because you can always take a query and say, how can we make this faster, or what can we do to make it faster? There's loads of tricks and things in Oracle database to do that. The question is it worth your time? And really, that's the question you should ask. How much effort, is this high enough priority compared to the 5,000 other things your boss is asking you to do to optimize it further? And I don't think there is a better, a right answer to this question. Different people have different perspectives. What matters is that you speak with whoever is using the application or whoever owns the application, and whether they are happy performance. If other people have other perspectives, please let us know. Okay, so at this point, let's jump into some demos. And we're going to walk through some bad plans, some plans that are not quite right. So let me just make sure I'm connected. My thing is still live, so let's give that a second. What other questions or comments do people have before I jump into these? Okay, so we've got that up. All right, so I have got a 4-table join here. So we've got a whole bunch of information. So someone was asking earlier about getting the plans in SQL Developer. So up on the top here, there's a thing called Auto Trace, which by default is the F6 button. And when we run that, I'll show you what happens. So I'll hit that little button up there, Auto Trace, zoom in a little bit so you can see. So that's what you want to hit, or hit F6. It will get the execution plan for your query. And we've got a plan that looks a little bit like this. Okay, so let's zoom in on this a little bit, so hopefully you can all see what's going on. I think this is not a good plan. So who can see something that's not great here, or something suspicious, and what might we do about it? Any suggestions, comments, ideas? Cartesian join, yeah, that's a good thing. Yeah, merge join. Yeah, it's a bit suspicious, isn't it? So we've got this merge join. First thing we're doing is reading the rows out of the bricks table. Now the thing here is the database thinks we are going to get 1 row out of this table, cardinality of 1. But in fact, we actually get 24. So that's not good. So there's a misestimate. So if we look look at those two columns, cardinality versus last output rows, expected 1, but actually we've got 24. Now, it's worth noting that if this query really does return just 1 row, and we're joining it to every other row in the other table, a merge join Cartesian can be the fastest way to do this, but it relies on us getting exactly 1 row out of that table. We've got 24. Side effect of that is, if you can see over on just below it, we've got the buffer sort. We do that 24 times. Well, that's what the plan tells us. So we're doing a lot of extra work there. So this is, definitely a sign that something's out. So we've got a big misestimation in how many rows we're getting. So how might we fix this? Any suggestions or comments on what we might do? Gather stats. There we go. There we go. That's the thing I was looking for. So I fixed the stats for these tables specifically to kind of get this kind of bad plan, but it's possible that you might have something like this. So let's just go down and gather the statistics for that. I'll just pin this plan here just for a second. So we've gathered the statistics that ran. Yes, that ran. And I'll get the execution plan again. We'll rerun auto trace. So we do that, and now, oh, hang on. Did I actually run that? Let me just make sure I gather those stats, and hopefully now this time it will do. There we go. So now we look at that. The merge join Cartesian is gone. We've replaced it with a whole bunch of hash joins, and at this point, those cardinalities and those output rows basically all match. If you've got good memory, you might recall this looks suspiciously like that 4-table join plan I showed you earlier, and that's because it is. I lifted the figures straight from that. So we can see we've got things going on there. So one of the reasons I pinned this is in SQL Developer, we've got our 2 plans side by side. We can do a little compare here and see what the differences are. So we can compare those, and little things highlighted in red show us where the differences are. Just quickly, Judith, you had a question about filters and so on. So you can see in this plan here, below each thing, actually, if I just expand predicates and projections like that, below each thing, we've got access predicates. So that's showing us what thing we're doing for each of these joins, basically which join is happening here at each step. So Hegarty, does the auto trace feature show the cost of each steps in the plan? Is cost a still good guide for areas to focus on? So first point part of that question. If we go into the preferences, so let's just show that again. Tools, preferences, search for auto trace. There is a whole stack of things that you can show here. I've focused on the core things to keep it simple, but there is buckets of things you can display. Third in the list, cost. You notice I've unchecked that. Why? Well, partly I think actually it's not that helpful generally. I think people get a bit too hung up on this cost and say, oh, the cost is bad, blah, 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 blah. And it's, for the most part, there's not much you can really do about it. Things like, can we process less data? Can we get the estimates right? Are things you can change. The cost is a consequence of those. So generally, I avoid looking at that. If you want to look at it, you certainly can do. Okay. Other questions, comments at this point? One other thing I mentioned quickly while we're here. So look at those last times. Those values there are in microseconds. So remember I said hundredths of a second might be not granular enough. It's nowhere near enough here. So we can see that's 1,000 microseconds for the whole query, which is a thousandth of a second. So certainly for fast queries, this display in SQL Developer is much more useful for getting these time breakdowns. Okay. Is last elapsed time cumulative? Yes, it is. So one of the things, if you are just doing it yourself, the nice thing about SQL Developer is you can expand and collapse these things. So if we collapse those down, this hash join here, time here of 2,500 is, you have to subtract off this 797 plus 35, so 800 odd microseconds. So 2,400 minus 800 took 1,600 odd microseconds to process the hash join itself. So yes, elapsed time is cumulative. I say quite easy to spot in SQL Developer just by collapsing everything beneath it, so you can then see what two direct children are. Same applies for these buffer gets operation here. Okay, let's move on. Let's close this down. So next, messed my query up there. So I've got another query here, and I'll get another plan for this. And thinky. What I've got here is a hash join of the two tables, and I'll just run the query itself so you can see what we get. We get just one row in the output. So if we kind of glance over this plan, I'll shrink things down a bit to help you see what's going on here. Any thoughts about this? Comments, suggestions, what we might do to improve this query? So we're just full scanning both tables and getting one row in the output. What do we think of this? Good, bad, indifferent? Everyone thinking hard, hopefully. Oh, not sure what you're saying there, Antonis. I can't read that writing. Better to avoid natural join. That's besides the point. So index, create an index. Very good. Yes. So one of the things said before is look at the I/O. So if we look at the CR buffer gets consistent reads, we're full scanning 6 gets to read one row. Bit suspicious, right? When you've got really you want to read multiple rows without one I/O, not have multiple I/Os to read one row. If you're doing more I/O than the query, than the query's outputting, it's a sign that maybe there's something you can do to make it run faster. So we're getting one row from both those tables, 6 gets from each, 12 in total. So what can we do? Add some indexes. Great suggestion from all of you. So brick ID is in fact the primary key. I've been very lax, not defined it. Very naughty me. Let's create those indexes. Let's just pin that and run the query again. And now we look at that and we look at what we're doing here. So cardinality, output rows 1, 1, 1, 1. Everything lines up nicely. Buffer gets has dropped down considerably just to 4. So notice we've got 1 get to read the index and 1 get to read the row. So that's 2 for each, giving 4 in total. So this gives a big saving compared to the 12 that we had previously. Hegarty, our index is still useful on Exadata hosted databases. That's a question which has a bigger answer than we've really got time to go into. The short answer is, if you are returning, basically, if you only return 1 or 2 rows from a table, you probably always want to use an index. Beyond that, it all gets a bit fuzzy. When it comes to Exadata, there are a lot more optimizations which make full scans a lot more efficient. But primary key lookups basically always want to use an index. Other types of queries, it depends, and there's a lot that can be discussed on that. Okay, John, do we have to gather stats once index is created? So creating the index will in fact gather stats as well. So you don't need to have a separate stats gathering, and that's been true for a long time. Okay, so there's one. So good questions, folks. Keep them coming. But there's one other example I wanted to show you before we wrap up, and that was this Scalar Subquery. So let's run it and see the plan we get here. So let's get that auto trace, pin it. So we've got, see that sort, table access full sort that we had there. And notice I said we would do that full scan multiple times. We know that because we can see from that last start column, we're doing it 3 times. And it says output 24 rows, cardinality of 8. 3 times 8 is 24. So estimate's right. We're getting 24 rows because we're doing this thing multiple times. We're reading all the rows in the table. And that's happening once for each row we get out the colors table. So we're doing a lot of unnecessary work here. One other thing to mention here, notice the top CR buffer gets listed there as 6, and below it we have 18. So this is where things get slightly confusing again. So the total here, the 6 is from processing the from clause essentially, and the 18 is from processing the Scalar subquery. To find the total, you need to add those together to get 24. Luckily, SQL Developer does also have all the stats listed here. I'll just bring this over so it's a bit easier to see, but you can see consistent gets 24 there, hopefully. So again, with Scalar subqueries, it can be a bit tricky to figure these out. So what can we do for this query? How can we improve this? So while you type in your suggestions, I see there's some other comments come in. So let me know what you think about improving that Scalar subquery where I address these other points. So Ravi, are covering indexes recommended, or can it have some pitfalls? Again, it's one of those almost a session in its own right questions. So a covering index, for those of you not familiar, covering index is one where all the columns in your query appear in the index, which means the database can answer the query just reading the data from the index. It doesn't have to access the table altogether. This can be a big saving because indexes are usually much smaller data structures than the table. So a couple of things. First up, we can search the index efficiently rather than doing a full scan, and it's a smaller data structure. So they can be very useful. The downside is, of course, you're going to have a lot of different queries. Are you really going to create a covering index for every single one? Probably not. That's probably not a good idea. Also, at some point, the covering index, the size of it becomes close to, or even potentially bigger than the table itself. You know, if you've just taken all the columns from your table and stuck them in the index, you know, has that really helped you in any meaningful way, right? In which case, you might be looking at something more like an index organized table. So the pitfalls there really are just that you end up over-indexing. You create an index for every single query, which is, well, it uses a lot of space, gives the optimizer headaches because it then becomes challenging, or can become challenging, to choose the right index. And at some point, it actually is no more efficient than a full table scan if you include most or all the columns from the table in the index. So yeah, it's ultimately, you know, if you've got a query where performance absolutely matters, it's worth doing, but I wouldn't do it for every single query. So Judith, except for function-based indexes where you need the column stats for the new virtual columns. Maybe, okay, I guess you're referring to the gather stats there. Yes, good point. And maybe transform the Scalar subquery into an inline aggregate view and join. Yes, so first thing we could try is turn this into a join. Now, in order to turn this into an inner join, do note, so this query will return every row from the colors and then find the matching ones in bricks. If some of the rows in this table, some of those colors are null, this will return nothing. So to get the same result, either we have to use an outer join or make that mandatory. So let's run this query and we'll get some details in a second. And now we can see we've got an index scan of our colors. So we've gone from 2 full scans to a full scan and an index scan. That's a good saving. And our buffer gets has dropped considerably, down to 8. And notice we're doing well, actually, we are doing this last thing 3 times, but much more improved. Judith, aggregate the bricks table alone. Well, there's a good point. There's, you know, if this is our entire query, we're only getting the count of things out of bricks, and the color is mandatory in the bricks table, we could just do this. We don't even need to read the colors table, right? So we could just simplify the query to this altogether. And we've got just this, making things even faster. But we can still do even better. We could create an index on that. Now, at this point, if we check what's happened after we got that index, we've still got a full scan here. And we'll go, well, we're just reading that color. Why have we got a full scan? Well, in Oracle database, wholly null entries are not included in a B tree, a standard index. So if there are any nulls in here, they are not going to be included in this index, and we get the wrong result by scanning it. So either we could do this, add a where is not null, and if we run our query again, hopefully we'll get a nice index scan, getting even faster again, down to just one get. Or even better, assuming that color is mandatory, importance of defining good constraints, we can set that up. And if we now, I'll just make sure I pin that to show what's going on, run that again, and we will get the full scan of the index again. And there we go. So we've improved things. Notice at this point, even if we go back and run the Scalar subquery again, we've now dropped down the work we did considerably. I'll compare that with the first one. Creating the indexes and so on has given us some advantage, gone from full scan to an index scan, and our work has gone from 24 gets down to 8. So we've thirded our work roughly. Would count ID have done the job? No, because we're grouping by color. So you still need, I'm not sure where you're saying count ID exactly, but the thing is here, we're grouping by color. So unless we've got an index on color, we would have to read the data from the table to do that. All right, then. We're getting close to the hour. So I wanted to just jump back here briefly. So a couple of things to finish up. So where do we go from here? So I've shown you some ways of getting an execution plan. I've also got a blog post that discusses how to use DBMS Expand, also uses SQL Developer. Also talks about a couple of other techniques, notably SQL Monitor. That's probably actually one of my favorite techniques, but it does have licensing implications, and it only kicks in by default for slow queries. Those in parallel will take longer than 5 seconds. So check that out if you want to look more background about how to create these plans. To Peter or anyone else who is interested in how to get the scripts, get the plans and so on, or recreate what I've just talked about, got live SQL script there. You can access that, so head out to that. So Judith, yes, you can use the hint to make the SQL Monitor kick in always. Bit tricky if, this is code in an application somewhere. It's not always possible to go through and fiddle around with that, but good point. Finally, just start playing around. A lot of what's going to help you learn how this works is just fiddling with things. Get a complicated query, look at its plan, add some indexes, drop some indexes, gather stats, fiddle with the stats to set them so they're wrong or right, and see what happens. Just start playing around and compare the plans, see what happens in different scenarios, and you'll start to get a feel for when things are good and bad and so on. Okay, so Ravi, you requested a session to do how to read a parallel execution plans. I'll add that to the list. They are a bit more complicated. I'll have that to think about. If you've huge topic to hint about using hints, I'll give you the short answer. Don't, right, Judith? I think that's the only session I'm going to give on using hints. Don't use hints. Okay, that's a bit simplified, but really, if you're thinking about using hints, really you should be looking at things like SQL plan management. I recognize that there are some hints, things like gather plan statistics, which don't actually change the plan but are still useful, but I'm not going to do a session on hints, okay? If you have any other questions, feel free to get in touch, either via the AskTOM site session itself, email me, chris.saxon@oracle.com, get in touch on Twitter, @ChrisRSaxon, or put some comments in chat now. I'll hang around for a second or two if there's anything else you want to say but to finish up. But I really hope you enjoyed this. More importantly, I hope you learned something and found it useful. So thank you all for joining me. Hope you have a great Christmas, holidays, festive season, whatever we do to celebrate. And I hope to see you all sometime in 2020. Goodbye.